guys can see my screen very clearly. So I have finished this one, and it works very well. And now I'm going to start from scratch and show you and walk you guys through. This is modeling process. Now this is model 1. Let me create another model. So model 2, and create this model 2. Model 2 I will for the demo, for the demonstration, and show me. Let me show you. Let me change the name and rename it demo. Okay, so for this one, so let's get started. Let's open this demo model and for the parts. And first of all, we need to define our parts, right? So these are the parts. Double click these parts, and so here's this dialog appears, and just part 1, and we only have one part, and we select 2D planar, and the deformable, and the shell, and this is the shell, and the approximate size here, because for our case, the length of the specimen equals 55 millimeter. So, and we can use 200 millimeter. I need to reiterate that ABAQUS does not have its own units. And so we need to define our own units. For our case, and we use this new force, we use Newton, and this is length, the dimension. The length we use millimeter. As a result, Young's modulus, the stress value you get, and everything that has the same unit as this is a stress, and you will see we will have megapascal. Okay, guys. So this is and what I told you, and why, and give you our first demo for our quiz 1. For this, here is the same thing. So we will use millimeter as a unit for the length, and we will use Newton as a unit and for the force, right? As a result, as I said, for the stress, Young's modulus, all these guys, and you need to enter the value in megapascal, and the value you get will be in megapascal as well. So we have is a 2D planar deformable shell, approximate size 200, and then we will be led to this interface. So now we want to draw the bottom line. Okay, so to draw the bottom line, and we use the line here and here, and I have draw a bottom line from here and to here. Right, I want to draw this one, and the reason is that there's a supporter, and there's a distance between the left edge and this left supporter, and they will have this is 6 millimeter. So it's a 6 millimeter. Then I go here. So this one and will be 21.5 millimeter. I'm going to dimension them later. Okay. So here this is symmetric, and 21. This one it will be 21.5 millimeter, and then go here. So this segment will be 6 millimeter again. So I go vertical and go all the way back to the left, and then we go here, go down. Now, I have drawn all these line segments. Let me, and this is the procedure, and then I'm going to dimension it. Okay, so dimension. As I said here, so the distance between the left edge and the left supporter is 6 millimeter. I'll enter 6. Enter. And then here for this one, and this 21.5 millimeter. And here is the same thing, and 21.5 millimeter. And for this one, we have this is 6 millimeter. 6 millimeter. Okay. This is for the bottom edge, and we have several segments, right? So for the height, this height, and the height is 10 centimeter. So from here to here, you cannot measure it, but you cannot dimension it. If you dimension it, the system will tell you, and you just over constraint this specimen. Okay, guys. And so this is pretty much what we have. We have all these this length 6, 21.5, 21.5. I mean, from this left supporter and to this right supporter, it is 43 millimeter. So this the height is 10, and so this is 6 again, between the right supporter and this right edge. So here you cannot dimension it anymore. As I said, if you dimension again, so the system will tell you that you just over constrained the system, you over constrained the specimen. Now, we have finished and draw this specimen, and then we can enter done. Okay, this is our this is our specimen. Then I'm going to create the partition. So create a partition, and here this create a partition. I want to create a two partition. I have two partitions, and first one is for the crack tape, which is in the middle, on this bottom edge, middle of the bottom edge. And then at this the crack tape, I have a tiny circle. So I'm going to show you guys here. So here is this one, partition face. Okay, partition face. Click it, and then we'll be led here, led to this interface. As I said, first partition is for the crack, and in the middle of the bottom edge here, this point. So let's use this one. Create lines for the line, and we go here, right? And then we draw a circle, a tiny circle, and then we draw a tiny circle. Okay, let me either escape and press the ESC, and then use this create a circle, and we use this center, use this crack tape as the center, right? Then we draw here and make sure your point is on this point. Okay, my mouse, this white point is on the vertical line. Okay, now I have finished, and I cancel this one, and then I dimension it. Okay, so dimension, and we use the same thing here. So dimension. So this one and is 2.0 millimeter, and the radius of this is a circle. Now the default value is 1.43, but we are asked to use 0.5 millimeter. Then we enter. Now this we have done this 0.5 millimeter, right? So this is our circle, and we have done it. And sketch partition geometry we done, right? Okay, guys, so we've done this. Now you can see we have this partition, and we have this this is a circle. Okay, guys, we're done. And then we define the crack, right? We define the crack. And how to define the crack? No, I'm sorry. Because this one we need to start from zero, from the scratch. So these are our parts. The second one is the material elasticity only, elastic, and Young's modulus, and we have 200 gigapascal. We have 200 gigapascal equals 2 E. Okay, here I'm sorry. And 2 E. This is 5. You should know that this is the unit is megapascal. and Poisson's ratio is 0.3, right? And then click OK. Now material, after we defined this material, and then we need to define the section. And homogeneous, continual, and the material, and toggle this on, and plane strain. We are asked to use to model this plane strain, okay? So this one we use 1, and click OK. Now we need to come back and to specify the section for this part. And section assignment, and select the region, okay? So because we have partition it, we have 2 regions. One is the region inside within this small circle. Another one is the rest of this problem domain. And we use a shift, this part, right? See? And then this part, and then we don't want to create a set, and then we're done. And which section? Because we only have defined one section, section 1, so we just select section 1, and click OK. Now this is our this green means that we have assigned this section properly correctly assigned a section on all these the domains. Then we're done. Right? And then assembly, go here, assembly, instance, and so yes, parts, and we use the independent mesh. Okay, so this is highly suggested. However, you can come back to toggle this on and off if there's a need. And OK. After here, and we can define the define the crack. And how to define the crack? And we go here. Okay, so this is assembly. So these are engineering features, right? So you can see engineering features here. And open this one, so crack. And you click the crack. And click, this is click crack, double click crack. So here this dialog appears. And name crack 1, because we only have 1 crack. And crack 1, and with the type, we use the contour integral. Right? And then press continue. And then this dialog will appear. Select the cracked front. First, the contour in region. So for this one, we select this is crack front. Crack front is a crack tip. And we select this is a crack tip. And we can enlarge it actually. Okay, and then we press done. And so we will be asked to select this one, specify crack extension direction using normal to crack plane or Q vector. And we will use this one, Q vector. And then after you select the Q vector, and you need to select the start point, okay, for the Q vector and end point for the Q vector, because a vector can be defined by 2 independent points. So for our case, so this Q vector is vertical. So we can select, so this is our start point, right? Then end point is where end here. Now, so this dialog appears. So we can see the Q vector is 0, 1, 0. It's y in the y direction. So it's correct. And any questions so far? Okay, I'm sorry, because this is demo, you cannot answer my questions. And then this is the tab called singularity. Okay, and for our case, so this one and set the mid side node parameter, and we select 0.25. So remember, this is my demonstration. After I finish this one, you need to do your own work, and you will do the parametric study, and you will be asked to use several other parameters for this mid side node parameter, and also you will use either use this option or that option. So for our case, for this demonstration, and I'll just use For this one, we use 0.25, and for this option, we select in the middle. Okay, as I said, and after I finish this one, I give you results, but there are several other parameters you need to change and to get different models, and then you compare the results, and you will obtain from these different models and to give some insightful conclusions. Okay, so for our demonstration, we use 0.25, and here we use collapsed element side and single node. Right? And so you will be asked to use either this one or this one, and with other different models, the different these parameters, and then click OK. So this introduces a square root singularity as a crack tip, and we click OK. Now this is a crack. Okay, so we have this crack here, and then then we go to this main menu and special, right? The crack and assign seam. We use the seam, and so here select the entities to be modeled as a seam, and select entities to be modeled as a seam. And which one we want to select? And we want to select these two edges. And so here also this one edge, and so also this edge within this is a tiny circle. So we use the Shift, select this one, and select this one. No, I'm sorry. Select the, yes, just one second. Let me redo it. Let me redo it. I'll make sure I do everything correct. Assign seam, right? So Shift, I can enlarge it. Shift, I select this edge. I select this edge. Okay, now done. Now you can see this is will be treated as a crack, and we save. And I can I use this one and feed all the feature view. And we have this is a crack. Okay. Then after I finish it here, I can define the output. What kind of output I want to have. So go here, assembly, right? No assembly. So this is the field history, and I want the history output requests. History output requests. I double click it. And for here, I define the control integral history. Okay, I select control. I define this one as a control integral history. Oh, okay, I'm sorry. So the step, okay, we define a step here. And step one, and after the initial one, static general, and toggle this on, nonlinear geometrical nonlinearity, toggle this on, and click OK. Now, then by default, and we will have H output one, but we want to define another one, and this is for contour integral history. This is our first the user defined history. Okay, I continue, and so then this dialog appears. For the domain, you can select a whole model, but now for our case, we can just select the crack. Okay, for the select the crack. Which crack? We only define the crack one. And then here, number of contours, we select 5. Okay, number of contours, and we select 5. For this case, we require J integral. So this is our J integral. So every n increments, n equals 1. So this is very cool. You can change this one, but I would suggest you use 1. This is 5, and select the J integral. So this is our first user-defined. This is a history request. And then I select another one. Double click. This time with stress intensity factor. And continue. Now this time also for the crack. Crack 1, number of contours 5. Okay. And stress intensity factor. We select the stress intensity factor using maximum tangential stress. And okay. Now you can double check. Edit. So 5 J integral for this one. 5 stress intensity factor, and click OK. Now we don't forget to save it. Right? And then, we need to end these boundary conditions. Go here, boundary condition. So boundary condition 1, and so this is for the left supporter and the right supporter. We have 2 supporters. For the left supporter, and we want that point is fixed in both X and Y direction. For the right supporter, we just want to fix that point in the X direction. Okay, so boundary condition 1, displacement rotation, and continue, and we select this is our left pointer, left supporter, then done. For this case, U1 equals 0, you cannot, and U2 equals 0, right? So they can rotate freely and about this z-axis. So okay. And then we create another boundary condition, displacement rotation, continue, and for this, and done. And so we have, and for this right one, and we just make sure this guy will not move in the U2 direction, right? So this is okay now. So we save. And then we want to make sure this one is added in the correct step. So here, move left. And then we apply this load. This kind of loads, we apply this bending moment at these 2 ends. So this applying bending moments to a problem domain is kind of the tricky. Okay, so this is need special techniques. I'm going to show you guys. What I want to do is that I will specify a reference point at the center of left edge and use this reference point to represent this whole left edge. And similarly, and I will create a reference point at the center of right edge and use this reference point to represent the right edge. Okay, let me do this one first. For here, so here tools and reference point. So I'll see. So this one, the center point of left edge is appeared. I select this one. So RP1, okay, and then I select here as RP2. So we have 2 reference points, and then I go back to assembly. Okay, go back to assembly. So this is a set. I create 2 sets. One set one set is for the left edge, another set is for the right edge. I'm go here, double click. Set 1, I will use this left edge. Okay, so select the geometry for the set. I select here. Done. Right? And then do the same thing. Set 2 is the right edge. And continue. And select the geometry for the set. I select this is a right edge. And then done. So I have finished these two sets. The save. Then I need to constrain and the constraints here. Constraint, double click these constraints here. So this I use coupling, okay? Coupling. So constraint 1 for left edge, I use a reference point to represent the whole left edge. The same thing for the reference point on the right edge, and this reference point will be used to represent, and this is the whole right edge. I'll say constraint 1, right? I'll say left edge, coupling, continue. So see, select the constraint point, control points. So I select this reference point. This reference point is highlighted. Done. Then select the constraint region type. You want to use this control point to represent what? I select node this region, okay? And set, because I created the two sets already. Left edge, continue. So here comes out. And so kinematic, we use a kinematic coupling. So this one will be okay. And that's okay. Right? And then I add another constraint, double click, and constraint 2, I just see right edge. Also coupling, continue. And select, just follow this is instruction. Select the constraint control point. I want to select the right reference point. Done. So select the constraint region type, and I select the node region, and select the sites because I have defined the two sets. One is for left edge, the second one is for the right edge. So right edge. Now continue. And kinematic. Okay. Yeah, you can see. Now we have our reference point 1, and this is our reference point 2. Okay, guys. And so after we define this is a coupling, and we can go back to define our loads. Load 1, and this load 1 will be the moment applied on the reference point 1. Right? So reference moment, click, continue. Let's say left. Continue. And select the points for the load. I select this reference point. Done. So what? So this is on CM3. Okay, so guys. So you need to know that. And so this is we have the negative. Okay, this is negative, positive. How when we should use negative, when we should use positive. And this bending moment is a moment rotate clockwise, the negative. Counterclockwise is positive. Okay, so be very, very careful. So for here, and we just want to bend this system, the beam this way. So on my left edge, it will moment will be clockwise. So this is negative. Negative. The value is let me look at the value. The value is 1075 Newton meter. Okay, as I told you guys at the very beginning, the force is used in Newton, and the length is used in millimeter. So this one, and you need to be very, very careful. This 1075 is in the unit of Newton multiplied by millimeter. Okay. And then another load is a load right, the red point, red reference point. Moment, continue. So I select this one. Done. And so this CM3, now this time it is counterclockwise and should be positive 10.75, right? So this 10.75 and negative 10.75, and they are supposed to be the same in magnitude, 10.75. And then click OK. Now don't forget to save. So this is always a good habit to right-click it, manager, right? So make sure you apply the boundary, you apply the loads on the correct, on the appropriate these steps. These are correct. We only have one step, and I also suggest that you double check this one as well to make sure these boundary conditions are applied on the correct steps. We are okay now. So click save. Now next step will be the meshing. Okay, so next time will be mesh. So then we are going to mesh. Okay, so go. Here. So go here, mesh. Okay. How we want to mesh this for this one? Okay, so we have two regions, and one is the region within this. One is a region within this. This is tiny circle. Another region is outside the tiny circle within this the problem domain. So first we assign a global seed size of 1.0. So this icon seed the extents, right? And so we use 1.0 and then click OK. Here you can see the seeds, and then we assign these edge seeds because we have a tiny circle there. We assign the local edge seeds and to the circular region surrounding the crack tip. So seed for this one, seed edge. Where are we going to go? We need to enlarge it and then pen it. Okay, for here, for the circular edge, we are asked to specify 16 elements. We select the region to be assigned circle. Okay, Shift. This one, and this one, and then done. Then done by number, and we use 16. We use 16. No bias here, okay? So the 16, there is a constraint. There is a constraint there. And we say allow the number of elements to increase only. So we select this one. So they said this is not required, but will improve mesh quality in this case. Okay, we press OK. Now you can see these seeds. And then we specify 4 elements along the straight edge within the circular region. So this part. And also, you see, select the edge to be assigned local seeds here. Done. And so we basic and by number 4. no bias. Also constraint, we use this one. Okay, great, fine. Right? So then we assign the swept mesh control is here. Mesh control, assign mesh control, and select the region to be assigned mesh control. I told you guys, we have two. Circular region. Okay. So we have two regions. One is the circular region within the tiny circle, and one is outside the tiny circle. We select this one first. And fine. And then we select, we use this quadrilateral dominated, and we use this is and sweep. Right? For the within the tiny circle, we use quadrilateral dominated and the sweep, and then OK. Now, for other parts, for the part region outside this tiny circle, we use this one. Right? Done. Then we use quadrilateral. We use medium axis. And we will use the OK. Now we have assigned mesh control. Then we assign the elements. Assign the this one. We assign quadrilateral reduced to all region of the plate. We assign, use this one, assign element type, and the two regions, and both this region and this region. Fine. And we use quadrilateral. We use reduce integration. Okay, make sure this is plane string. So we'll have reduced integration. We use CPE8R. R means reduction. Right, so click OK. Okay, now, and then we can mesh, generate a mesh. Here, use this one. Mesh. Okay, to generate part distance, which includes these both two regions. Okay, so this is our mesh. Save it. Out of field view. Okay, guys. Any questions so far? Okay, if there's no question, let's query the elements attached to the crack tape to verify that their connectivity is that of a collapsed quadrilateral element with a repeated node at the crack tape. And we go tools, query, and let me enlarge it. And okay, this element, I select this one. Okay, you can see this is node connectivity 1010. So they have 1010. That means and the one two nodes are identical. It means that this is two nodes are identical. So that means two nodes are identical. That means this is the collapsed. This is because one end is as the correct tape. Okay, so we are good now. And then we can create a job, and then outfit. And then we can create a job 1. And I will say CPE HR focus demo and continue. Okay, I can submit it. Let's wait. You can see the monitor. See monitor how it goes. Okay. Successfully. Great. Okay, then we can check out the results. So here, so this is vomices, right? Once again, this deformation scale factor is too small. 1.0 is too small. So in order to see the deformation of this specimen, we need to use this one. No option, common. So uniform, we use 120. And yes, right? You can see this is correct, right? And then we can do the animation. And it's too fast. Let me go a little bit low. That's good, right? Okay, that's great. And save it. And then we can do the post-processing. We can do the post-processing. We can see this one. This is our. We can see the vomices stress. We can see other stresses. And we can see S11. Okay. And we can see S22. We can see S33. Now we can see S12. You can see other variables also. You can see this displacement, U2, right? And we can see a lot of other things. And then next, we can identify the domain for each contour. And in the result, this one, we expand node set. Okay, go here. Node set. Node set here. We have the contours here. So you can see for this contour, we pan this one a little bit. So this is our contour 1, which is a point. So these are contour 2, see? Contour 3, contour 4, contour 5, right? Beautiful, isn't it? And for this one, the same contour. It's very beautiful. I like it very much. So this one. For this one. No set. Okay. So and then we can get the J value. It's a J value. And go here. History output. For here, we have J value. Okay, so J value. You can have J So this is J value, this is J value, and this J value, and this J value. And we can and just put them together and shift, using shift, then plot. So they are, see, you can see these values, and they are converging, you see? They're very, very close. You see that, right? So you see, this value 1.32, and these three digits are the same, and they are very, very close. And we save. And then K matrix. No, I'm sorry. There's a stress intensity factor. So for here, 1, 2, 3, 4, 5. And we can see this value, okay? So this is value, and this value is for the control 1, which is a point. It is not correct. So this is point 2. This is point 2. This is control 2. Control 3. Control 4. Control 5. Okay, guys? So here. We can just draw them, plot them together. Okay? You can see this value. So this is our first value. For the first control, which is 1 point, it is not correct. So we focus on this. This is our value. Okay, guys? And so when you fill out this is the table, I want you guys to use the J value, use the K value from the contour 3, contour 4, contour 5, and for these 3 values, and then take the average, and then use that average value and to enter into this table. Okay, guys? So don't use the stress intensity vector factor value obtained from the first contour. First contour is just a 1 point correct T. It's not correct. Okay, guys? And I hope you guys have a lot of fun with this ABAQUS modeling, as I said, and you will do the parametric study and change this the several values. Okay, so change the mid set node parameter, and also change the collapsed element set and single mode or this duplicate mode, and to see how these 2 factors affect the final results. Also, so this is a focused the mesh, and you need to do this rectangular, the unfocused mesh. And how to do the unfocused mesh, it is given in detail in this, for this is handout. And you need to do all these things by yourself. Okay, guys? The deliverables will be first, and you give me 1, 2, 3, 4, 5. You give me 5 models, and within 1 CE file, 1 JNL file. And just as for my case, I have 2 models here, right? So I have 2 models, demo and model 1. For your case, you can select other 3 models and give me your file, 1 CE file, 1 JNL file, right, guys? And so these models, they have different parameters. And this is our first deliverable. And second deliverable is the table. And you need to enter this table, and based on what you get, the value you get for your KI, as I said, you just use the average of the KI value for the contour 3, contour 4, and to contour 5, and then enter this value to this table. So I want you guys give me an Excel file or Word file, but make sure you give me CE and JNL file for all your 5 models. And these 5 models must be within 1 CE file and 1 JNL file. Okay, guys? And so that is easy for me and to grade. Well, guys, I think this is pretty much on what I have, and I hope you guys have a lot of fun with it. And so I'm going to post this video online, and also this is the computational solid mechanics the handout online as well. So the quiz 2, the problem statement is at the very end.